Welcome again to the topic slope and deflection of statically indeterminate beams using the integration method. In the previous class, we solved the cantilever beam having triangularly distributed load over it, and the triangularly distributed beam was subjected to it was a cantilever beam subjected to triangularly distributed load and having a roller support at one end. We have solved this question last time, but there is a little correction in this question. As far as the correction is concerned, the correction is in this equation. There's a correction in this equation. As far as this question is concerned, in this question we are given a triangularly distributed load, and the load value at x is equal to L is W naught. So what we do in order to find the bending moment of this beam, we are cutting the beam at some distance x from the free end. From here, we are cutting the beam at a distance x. That's what's given here. We know over this span x, over this span, there will be the triangularly distributed load because we have taken a section here. So this load is on the beam. As far as this load is concerned, this load will be acting at the centroid of the beam, that is at the centroid, and the magnitude of the load will be equal to the area under the load diagram. Area under the load diagram, we have to first of all we need to find it. We have already said that when the value of x is equal to L, when we have the value of the length is L, at that time the value of the load is W naught. At that time the value of the load is W naught. When the length is 1 unit, at that time the value of the load will be W naught divided by L. Now when you are at a distance x, at that time the value of the load will be W naught by L into x. That is what is given here. This is the value of the load at this end. Okay. Therefore, area under this triangle will be half of base. Its base is x multiplied by perpendicular, that is W naught by L. That is W naught by L into x. That is equal to W naught x square by 2L. That is W naught x square by 2L as is given here. And this load will be acting at the centroid. We know from the 90-degree angle, the centroid is at a distance 1/3 of the base. The total base is x. Therefore, the distance of the centroid from the perpendicular end is 1/3 of the x. That is given here, 1/3 of x. Therefore, distance from here to here will be 2/3 of x. Now, when we write the moment equation, we have to write the moment equation. First of all, we start the equilibrium equations by writing the equilibrium for forces. We have Ay acting upwards. Ay, I also said that you can write this Ay as a reaction at end A. Okay, you can write this as Ra as well. It's your nomenclature. You are free enough to choose it. This is Ay acting upwards. We are taking it positive. We are having V acting downwards. We'll write this as minus V. We are having this load 1/2 W naught x square by L acting downwards. We'll take as negative. This is 1/2 W naught x square by L. This is acting downwards. There is no other force acting. Therefore, the summation has to be equal to 0. Therefore, from this equation, we'll get the value of V. As far as V is concerned, V is equal to Ay minus 1/2 W naught x square by L. This is the value of our V. Now, we have obtained the value of V. This is from the first equation of equilibrium. Now we will take up moments about an axis passing through point A. When we take up the moments about an axis passing through point A, first of all, we have the bending moment M. We'll write this as M. This M is anti-clockwise. We are taking this positive. We have the moment because of this V. This V is trying to rotate the beam in clockwise direction. This will be minus Vx. And we have the moment because of this 1/2 W naught. This is also trying to rotate the beam in clockwise direction. Its moment will also be negative, be 1/2 W naught x square by L. This is the force, okay, multiplied by force arm. That is 2/3 of x. That's 2/3 of x. So this 2 and 2 will cancel. So as far as M is concerned, the value of the M will come out equal. Our M is equal our m is equal to v into x. It's v into x, and we have plus w naught x cube w naught x cube by 3 times l. Now we know the value of v. Substitute the value of v in this equation. We will obtain the value of m as the value of m will be equal. We'll get m is equal to v into x. As far as v is concerned, v is equal to ay. It is ay minus w naught x square by 2l multiplied by this x. So this is multiplied by x plus w naught x cube by 3l. So w naught x cube by 3 times l. So that will be equal to m will be equal m will come out equal to ay. We are writing ay minus this is w naught x square by 2l into x. That is w naught x cube by 2l plus w naught x cube by 3l, which can be written as m will become equal to ay minus w naught x cube by l. Internally it will be 1 by 2 minus 1 by 3. That is 1 by 2 minus 1 by 2 is 1 by 2 minus 1 by 3 is 1 by 6. So we'll get m will come out equal, m will be equal to ay minus, this is 1 by 6. It will be in multiplication of this. It will be 1 by 6
सर x है ना ay के साथ भी मल्टीप्लाई में
x cube by l. It will be ay into x, ay into x, ay into x. Okay, so m will become equal to ay into x minus 1 by 6 w naught x cube by l. This is the value of the bending moment, and this is fine. Okay, I had a guess that this is not correct. This is okay. Okay, this is the value of the bending moment. M is equal to ayx. We are also having ayx minus 1 by 6 minus 1 by 6 w naught x cube by l. This is okay. Okay, then after writing this much, as we have done in the previous class, we have to write down the equation of the moment curvature relationship. The moment curvature relationship is ai nu d2 nu by dx2 is equal to m. As far as our m is concerned, these are the values of our m. Substitute the value of m, ayx. Okay, so first integration, you will get first constant of integration. Integrated again, you will get first constant of integration multiplied with x, and second constant of integration c2. Then I had already said what we are looking for are the boundary conditions. As far as the boundary conditions are concerned, the boundary conditions that we have in this problem are, look at that curve. Look at the curve. At x is equal to 0, the point x is equal to a before the application of load was here. After the application of load, the point will continue to be here. So we'll write at x is equal to 0. At x is equal to 0, the value of our deflection is equal to 0. This is one. Same is the case with this, x is equal to l. At x is equal to l, the value of our deflection is equal, the value of our deflection is 0. As well as for cantilever beam, this point is very, very important. Not only this, these are deflections. As far as the slope of the curve is concerned, as far as at x is equal to l, at x is equal to l, the value of the slope, that is d nu by dx, the value of the slope at x is equal to l is also equal to 0. This is also equal to 0. You know why? Because as the curve, if you look at the deflection curve, its deflection curve is essentially like this. So we can obtain the deflection curve with the help of simulation softwares, like we can do it in ANSYS. Okay, so as far as the deflection curve is concerned, its deflection curve is like this. As far as point B is concerned, ahead of point B, okay, there are few points. Ahead of point B, there are few points, like here. Ahead of point B, there are few points which do not actually move, which do not translate, which do not undergo any deflection. Okay, so if you draw the tangent, as I said in the last lecture as well, if you draw the tangent at these points, its tangent before the application of load will be in this direction, and after the application of the load, okay, its tangent will still be in this direction. Okay, this is not the case here. If you draw the tangent to the curve at point A, its tangent will be like this. Okay, but look here, the slope here is 0. It's parallel to the x-axis. That's why we say that the value of d nu by dx, the value of d nu by dx has to be equal to 0. Okay, so as we apply these boundary conditions, in these equations, you will get the value of your constants. We'll get the value of C2 is equal to 0, as I showed in the previous problem. We'll get the value of AY, as well as we got the value of C1. This is the reaction. And once you substitute the value of C1 back in this equation, you will get the equation of the deflection curve. This is what we have to actually essentially do in this problem. Same is the case, like we have this problem we have already done, and the boundary conditions that we have in this problem. In this problem, your first and foremost step will be obtaining the, for these statically indeterminate cases, you directly have to first of all write the bending moment equation. Once you write the bending moment equation, as this problem we have already solved, you will take a section somewhere at a distance x. Okay, take a section, write down the bending moment equation, and then write ei d2 nu by dx2, ei d2 nu by dx2 is equal to the value of the bending moment, whatever you find. Okay, and then perform the integrations. Keep on performing the integration. Since you have this is the second order differential equation. In order to obtain the value of nu, you have to perform two integrations. So you will get two constants of integration C1, and you will get two constants of integration C1 and C2. The constants of integration are obtained by applying the boundary conditions. As far as the boundary conditions in this problem are concerned, okay, you can directly write down the boundary conditions for these types of problems. The boundary conditions are, first boundary condition will be, first you have to write the boundary conditions in terms of slope and deflection. First write about the deflection. At x, since this is a fixed end, okay, at x is equal to a, x is equal to 0, that is at end A, there will be no deflection. You will write nu is equal to 0. Okay. Similarly, at x is equal to L, the value of your deflection is again equal to 0. There, these two ends are fixed. These points do not move. Wherever you have a fixed end, be careful about it. Wherever you have a fixed end, this fixed end is so much fixed. Okay, it is so much fixed that ahead of it, whatever be the points, up to a certain length ahead of this fixed support, the beam does not deflect. Okay, the beam does not deflect up to a certain length ahead of it. This is practically seen. Okay, ahead of it up to certain length, the beam does not deflect at all. Okay, so before the application of load, this length is like this length is straight, and after the application of load, this length continues to be straight, and this length continues to be straight. So if you draw the tangents, if we draw the tangents before the application of the load, up to this small length, the tangent was in this direction, and for here up to this small length, the tangent was in this direction. And after the application of the load, the tangent up to of this small length will be still in the same direction, and for the small length very close to this fixed end, the tangent will continue to be in the straight same direction. That's why we say at the fixed ends, be careful at the fixed ends, as far as at x is equal to 0, where you have the first fixed end, you have the slope is equal to 0, d nu by dx is equal to 0. Okay, this is third boundary condition. And x is equal to L, again you have d nu by dx is equal to 0, d nu by dx is equal to 0. So these are the four boundary conditions which you have to put in this the moment equation, the deflection equation, to get the values like it is here. Like here, just substitute these values like this. Okay, oh, sorry, like this. Okay, once you are performing the two integrations, once you have, first equation will be this. Okay, then once you are performing the first integration, you will get the first constant of integration. Perform the second, you will get C1 and C2 as two constants of integration. Okay, then apply the boundary conditions, whichever has been found, you will get the values, you will get your values. Okay, you will get the value of C1, you will get the value of C2. This is given here, C2 is equal to 0, C1 is also equal to 0. Okay, so you will get these values. Important in solving the statically indeterminate beams is obtaining the reactions. Okay, I hope I request you, please solve these questions, have a look of these questions, okay, so that we can, solve as many coming up problems as possible, okay. Let's solve few more questions. Let's solve these questions like we have given. Determine the reactions at the supports A and B, then draw the shear and moment diagram. EI is constant. Neglect the effect of the load. We are given, we have a beam problem like this. We have a beam which is fixed at both of its ends. It is subject to a concentrated load P at a distance 1/3 of the length from end A. Okay. Now at this point where it is subjected to concentrated load P, we have been asked to find the reactions. Okay. We have to find the reaction at end A and we have to find the reaction at end B. Now, how to find the reactions? First of all, we know as you separate the beam, important is as you separate the beam from its supports. They have support at end A, support and support at end A is fixed support. We know as far as a fixed support is concerned, it offers reactions. So we'll have reaction at end A, we'll have reaction at end B. Okay, we'll have two reactions. Apart from reaction at end A and reaction at end B, these are fixed supports. Okay, we know a fixed support is a support which offers two things. It offers the reaction as well as it offers the moment. So we'll have a moment here, we'll have a moment here. Okay, we'll have a moment here. We'll call this as moment MA. This is moment at end A, and this is moment at end B. We have been discussing this since the previous semester, that as far as a fixed support is concerned, like we discussed it in the cantilever. Okay, the cantilever offers reaction as well as it offers the moment. Now as far as this end is concerned, this end A is concerned, at end A you have reaction, we'll call this as RA. At end B you have reaction, you call this as RB. And apart from RA and RB, at end A you have moment in anti-clockwise direction, we call that as end MA. And at end B we have moment in anti-clockwise direction, clockwise direction. Let's suppose we call that as MD. So as far as our this redundants are concerned, as far as our reactions are concerned, we have RA, RB, there are two reactions. We have MA and MB, there are two more reactions. So total number of reactions that we have are 4. Okay. So in order to solve for 4 reactions, RA, RB, MA, and B, okay, in order to solve for 4 reactions, we need 4 equations. Okay, we should have 4 equations. Now we know, first of all, what we'll do, we have a concentrated load acting at end P. Let's go at end P, at a distance 1/3 of the L, we have a concentrated load. So we have to divide this beam into 2 separate sections, okay? Because at concentrated load, we know the bending moment changes sharply or abruptly. So our first analysis will be restricted for 0, going x greater than or equal to 0, less than or equal L by 3. Okay, so perform this analysis, that is go to a distance x, draw a section, and at that section write the shear force is V and bending moment is M. Okay, so shear force is V. So write down the equations. So as you write the equations of equilibrium, we have RA acting upwards, that is RA. We have V acting downwards, that is minus V is equal to 0. So from here we can directly get V is equal to RA. Okay, so from here we can directly get V is equal to RA in this case. Now taking moments about an axis passing through point A, we have the moment M, which we have assumed to be anti-clockwise. This is M. We have MA acting anti-clockwise, our assumption. So this is plus MA. And we have the moment because of this V, that will be, this is trying to rotate it clockwise, that will be minus V into X. That this is equal to 0. So as far as M is concerned, M becomes equal to V into X minus MA. Okay. As far as M is concerned, M becomes equal to V into X. V is equal to RA into X, minus MA. Okay. Now we know, as far as M is concerned, M is equal to EI D2 nu by dx2. EI D2 nu by dx2 is equal to the bending moment M, which is equal to RA into X minus MA. So perform the first integration. Once we perform the first integration, we'll get d nu by dx is equal to 1 by EI into RA x square by 2, minus MA into X, this is our first, this is d nu by dx. Sorry, plus we have to do plus the constant of integration. Sorry, because this is indefinite integral, it will have the constant of integration plus c1. Okay, c1 is the constant of integration. This is c1. Then again, we perform one more integration. So we'll write nu. Once you perform one more integration of d nu by dx, we'll get nu is equal to 1 by ei, 1 by ei ra x cube by 6, ra x cube by 6 minus ma square by 2 minus ma x square by 2 plus c1x plus one more constant of integration, that will be c2. So this is the equation of our deflection curve for what? For x going from 0 to x going to L by 3 for this curve. Now we'll go to the next region. As far as our next region is concerned, we'll be taking a section over here. Let's take a section here in this region. So let's say this distance is x. So let's suppose here shear force is V and here bending moment is M. So again, we'll do the same analysis for x greater than or equal to L by 3, for x greater than or equal to L by 3, L by 3 greater than or equal to x less than or equal to 2 times L by 3. Okay, for this, that's for this region. We can write down the equations of equilibrium. We have V acting downwards, we'll write this as minus V. We have RA acting upwards, that is plus RA, and we have this acting, we have RA acting down upwards, we'll write this as RA, and we have P acting downwards, we'll write this as minus P. Has to be equal to 0. Therefore, our V becomes equal to P minus RA. This is our value of V. Okay, we are done with the V. Now, as after doing away with the value of V, after writing the value of, this is our V. Now, after writing it V, we will take moments about an x is passing through pointing. We'll have moment M. So we're writing M. Moment because of this V will be clockwise. It will be V into X. And we'll be having moment because of this P clockwise. That will be minus P into its force arm. That is L by 3. That's minus P L by 3. And we're having moment at end A, that is plus MA. Okay. This has to be equal to 0. So we can directly write, as far as M is equal V into X. V is P minus RA. So it is PX minus RA into X minus RA into X minus PL by 3 minus PL by 3. So we are taking it, so it will be px minus this, so it is minus. So you are taking it on this side, it will plus, this will be minus ma. Okay, because you are taking it to the right hand side of the 0, the signs will change. Okay, so we know now, as far as this m is concerned, is ei d2 nu by dx2, ei d2 nu by dx2 is equal to m, that is equal to px minus rax plus pl by 3 minus ma. So perform the first integration, we'll get d nu by dx, is equal to px, that is px square by 2, it will be px square by 2 minus ra x square by 2 minus ra x square by 2 plus plx by 3 minus ma into x plus constant of integration c3. Okay, again perform the integration, we'll write nu is equal px cube, it is px cube by 6 minus ra x cube by 6 plus pl x square by 6 minus ma x square by 2 plus c3x plus c4 plus c3 into x plus c4. Okay, now we have 4 constants of integration. We have c1, c2, c3, c4. Therefore, we'll write down the equations of our, as far as the, we will write down the equations of our equations of what you call as the the boundary conditions. We have at x is equal to 0, the value of our deflection is equal to 0. Okay. At x is equal to 0, the slope is 0 because there's a fixed end. Okay. That is d nu by dx is equal to 0. D nu by dx is equal to 0. We have at x is equal to L, our deflection is equal to 0. Here at this point. At x is equal to L, the value of our slope is equal to 0. D nu by dx, d nu by dx is equal to 0. Okay. So substitute these four equations, substitute these four boundary conditions. X is equal to 0, nu is equal to 0. So this is to be substituted in this equation because x is equal to 0 is applicable in this region. X is equal to 0, d nu by dx is equal to 0. So you have to substitute x is equal to 0, d nu by dx is equal to 0 in this equation. X is equal to L, nu is equal to 0 is to be substituted in this equation. X is equal to L, d nu by dx is equal to 0 is to be substituted in this equation. So obtain the value of C3, C4, C1, C2 as well as the values of these reactions while taking these boundary conditions into consideration. From here onwards, substituting these boundary conditions in these equations and obtaining the values of reactions and these constants of integration, I am leaving as an exercise to the students. Thank you very much. Any question till now?